So we've defined the binomial distribution, and let's consider now each individual term. So here's the binomial distribution, and we've highlighted here in red the first term, and let's try to figure out what does this term represent. Well, what this represents in words, this bracket m in the top, and then n in the bottom, and then this other bracket. What this represents is m choose n, and that's how we say it in words. And what it indicates is the number of different ways of selecting n heads from m coin flips. And there's a formula for it. And how do we write it? Well, this symbol, this paren m over n and then paren, what this represents is just shorthand notation for this other expression, where we have this m factorial over n factorial and then m minus n factorial. Okay, so it's just shorthand notation. M choose n, we can write it out using this formula. And what is m with an exclamation point? It's not loud m, right? M, it's not that, it's m factorial. And what this indicates is m times m minus 1 times m minus 2 all the way up to 0. So we take m, we subtract 1 from it until we get all the way to 1, and then we multiply all of those values together. So that's what m factorial represents. And as an example, let's try to apply this. Let's compute 4 choose 1, which is written here in our symbol, and we've also written it out in words. So what does 4 choose 1 represent? Well, remember our formula. M choose n, it's m factorial over n factorial and then m minus n factorial. So what is m in this case? It's 4, and we're going to compute 4 factorial. N in this case is 1, so we'll compute 1 factorial. And then we have m minus n, 4 minus 1 factorial. So what does this equal? What is 4 factorial? Well, we're going to take 4 and multiply it by 4 minus 1, which is 3, and then times 3 minus 1, which is 2, and then times 1. So we multiply 4 times 3 times 2 times 1. 1 factorial is just 1, and then 4 minus 1 factorial is 3 factorial, which is 3 times 2 times 1. So we have these products in the numerator and denominator, and we can cancel some of these values, and we get 4. And let's compare this to our table. Remember, we initially considered the case of having 4 subintervals. So we're going to flip our coin 4 times, and we wanted to know how many ways could we observe heads. So we flip our coin 4 times. How many times do we get h one time? So we computed this, we actually tabulated this last time, and we can list all possible ways to get one h in 4 flips, and here they are. We flip our coin 4 times, and the h occurs first, or maybe it occurs second in the second row, or it occurs third, or occurs fourth. So we have these 4 possible ways, and these are the only possible ways where we can get h one time in 4 coin flips. It occurs at one of these positions. So here what we see in this brute force approach, where we actually list all the values, there are 4 different ways to get h one time in 4 coin flips. And the thing to note here is that these two values match. So this 4 choose 1 value, it tells us there are 4 possible ways of choosing one value in a list of 4. And here, by this brute force approach, we can consider these 4 coin flips and getting h only one time. And so the important point here is that this binomial, or this 4 choose 1 is giving us a representation of the number of different ways we can get different patterns. And we don't have to make tables anymore. So we'll avoid making this very long list. What about these second 2 terms? We have p to the n and then 1 minus p to the m minus n. So let's think about these terms. What do these represent in our binomial distribution? Well, we've said p is the probability of observing heads on a single coin flip, and n is the number of heads. So if we take p to the n, that represents the probability of heads occurring on n coin flips. We're thinking of these as independent. We multiply our probabilities together. We have n heads occurring in our list, so we multiply p together n times. So we get this p to the n. What about 1 minus p? What does that represent? Well, it represents 1 minus the probability of heads on a single coin flip. So 1 minus the probability of heads gives us the probability of tails, because remember, these two things must sum up to be 1. The probability of heads plus the probability of tails is 1. We're bound to get one of those 2 answers on every single coin flip, either heads or tails. And we're going to raise that 1 minus p, if we look at our expression, the 1 minus p to the m minus n. And can we interpret, what does m minus n represent? Well, m is the number of coin flips, and we're going to subtract from that the number of times we flip the coins, and we get h, heads. So the total number of coin flips minus the number of times we get heads, what's the only alternative? Well, it's equal to the number of tails that we observe when we flip our coin. We flip our coin m total times, we subtract the number of times we observe heads, and that gives us the number of tails. So we're going to take this probability, 1 minus p, the probability of tails, and raise it to the number of times that we observe tails. So what this represents is the probability of tails occurring on all of those m minus n coin flips. So hopefully what this gives us is some intuition for what this binomial expression represents. So we have the number of occurrences that we observe, this m choose n, the probability of observing heads n times, and then the probability of observing tails m minus n times. So this formula doesn't come out of the blue, it has some motivation. But let's try to apply it now. And we can ask this question, what is the probability of observing heads 1 time in 4 coin flips for a biased coin with probability of heads 0.1? So this is something we tried to compute last time by hand, you may remember. We have 4 subintervals, 4 coin flips, and we observe heads 1 time. So first let's define all of these symbols in our binomial distribution and try to apply it. So what is m? How many coin flips do we have? It's the total number of coin flips. In this case, there are 4. N, remember, represents the number of times that we observe h, heads. And in this case, we're observing heads 1 time, so we'll set that to 1. The probability, p is the probability of heads, and that here we've set that to be 0.1. We declare that here. The probability of heads is 0.1. So 1 minus p, it's the probability of tails. What is that in this case? It's 0.9. So we have all the values we need, and we can plug into our binomial distribution. So here we want to know the probability of observing heads once, n equals 1. So we plug into our binomial distribution. We have 4 choose 1, the probability of heads raised to the 1 power, because we get heads once, and then the probability of tails raised to the 4 minus 1 power. We can substitute in those values and compute it, and we get 0.2916. And maybe that number is encouraging. Let's compare it to our table, which we made painstakingly by hand last time in class. So here's our table where we indicate the number of spikes from 4 to 0 spikes, and we list all possible coin flips. And if we ask what is the probability of observing heads 1 time in 4 coin flips for this biased coin with a probability of 0.1, we can look in our table and we can ask, okay, we want to know the number of spikes is 1, we listed all possible outcomes here, and then we computed this probability. And we could compare this probability that we computed by hand, highlighted here in the red box, with the probability from the binomial distribution. And the important thing is we find that they match. So we can use our formula, and it's a much faster way to address and compute these probabilities than trying to list out all of these values by hand. And maybe we can make this list for the case of 4 coin flips, but what if we have many more coin flips? And we'll consider that in a moment. So the point of using the binomial distribution is it gives us the same result as that tabulation, except it's much easier to use. We no longer have to make these lists. And if we return to this original example, and we consider the case of 10 subintervals, so m equals 10, we can ask what's the probability of observing heads twice in 10 coin flips for a biased coin with the probability of heads 0.1. You may remember that we tried to begin tabulating these values. If we have 10 coin flips, what are all the possible patterns that'll give us heads once? Maybe we get 2 H's right at the beginning, or maybe they're somewhere in the middle at the end. It would be possible, I guess, to list all those values, although it would take us a long time and we're sure to make an error. So instead, we're not going to make this long tabulation list. Instead, we're going to use the binomial distribution, where we can consider the values that we need for m, n, p, and that's really all we need. So m in this case, it's the number of flips, is 10. We want to know n, the probability, or the number of times that we observe heads. And in this case, we're interested in observing heads twice, so n equals 2. The probability of heads, we've said, is 0.1, and so the probability of tails, 1 minus p, is 0.9. And if we plug all of those values into the binomial distribution, where here we want to know the probability of getting h 2 times in 10 flips, we can calculate out this number and we get a result, 0.19. And what's nice about this is it's easy. We don't require any tabulation, and we can immediately get the result using the binomial distribution. And what we'll consider in the next section is expanding this beyond 10 subintervals.